So today we have a Matthew from University of Waterloo. He's a graduate student of Jimgina. We talk about complex representable matrix. Right? Please.
Thank you. Well, thank you all for coming today. It's a real privilege for me to be here at the IBS, and I'd like to thank Professor Sang-Il for his hospitality and for inviting me to speak today. I'm especially excited to be giving this talk while I'm here, as it's based on joint work with my supervisor, Jim Gielen, and also with Rutger Campbell, whom I'm very happy to be visiting. And on top of that, all the research I'm presenting today relies very fundamentally on work of Ben Lund. So I felt that this was a very fitting talk for me to give during my visit here. So this is a talk about the average size of flats in real and complex representable matroids. And for the most part, I'm going to be talking about the average size of lines and the average size of planes. Okay, so for example, one of the main results I'll be discussing today is that if I give you a rank 4 real representable matroid and it's not the direct sum of two lines, then the average size of a plane in that matroid is bounded by an absolute constant. Okay, so I've drawn a picture of a direct sum of two lines right here, and as you can see in this matroid, every plane is forced to contain one of those two lines. And so, consequently, by making these lines both arbitrarily large, the average plane size becomes arbitrarily large.
To clarify, a rank 4 real representable matroid means a matroid where you can represent all the elements as vectors over the reals? Or?
I'll explain that in a second.
Okay, sorry.
Linda was just clarifying what I mean by rank 4 real representable matroid, and that is a perfectly good question to ask. So, as you can see, I've written this theorem in the language of matroid theory, but what really is going on here is this is all just geometry. So, in particular, if anyone here feels that they're not so familiar with matroids, in this talk you can think of a matroid as a very simple thing. So you can think of a matroid as just an arrangement of finitely many points in real space, together with the lines spanned by pairs of those points, the planes spanned by non-collinear triples of those points, and so on into higher dimensions. Now, the matroid itself is a combinatorial object, so the matroid is only concerned with this geometric data as it relates to that finite point set. So a plane in a matroid, for example, is not a plane in real space. It's the collection of points from the point set sitting in that plane. Okay, so this is what allows me to talk about the size of a plane in a matroid. It's just the number of points from that finite point set sitting in the plane. Okay, so what I've just described there is a real representable matroid, because you can embed the matroid, if you will, in real space. And a matroid that can be embedded in complex space is called complex representable. And I know from my title and abstract, I did indicate that this would be a talk about complex representable matroids, but I decided to just state the results and describe the techniques in the real case. And there's two reasons for me doing this. Real representable matroids are a lot more intuitive to think about, which is good for a talk. And B, as it turns out, with the techniques that we're using, in a way, once you prove something in the real case, everything kind of goes through in the complex case as well. And this is not by our doing. This is just because of the fact that we're using theorems that have been proved for both the real and complex representable matroids. Excuse me. Now, as a matter of fact, those theorems are quite a bit harder to prove in the complex case, but we don't need to worry about that. So what I'm trying to say is that you're not going to lose any understanding of our techniques by just thinking about real representable matroids. But yeah, so just talking about representability, like for example, what our theorem is saying geometrically is that there's this number n such that if I give you any arrangement of finitely many points in real space, so long as that set of points isn't all sitting in a plane or in the union of two lines, then the average number of points in a spanned plane is less than n. And we suspect that this number n could be proved to be quite low, like a single-digit number. But even if someone proved that n is less than 100, I would find that really exciting.
Also, if those points are like in general position, then n is like just 3, right?
Sorry?
I'm just trying to check.
Oh.
If those points are like in general position,
As in, like, with no sort of dependencies between? Yeah,
three,
sure.
right?
Yeah. So that's, so what you're describing is a uniform matroid where all the non-trivial flats just form independent sets, and in that case, the average is really easy. But you can get, with matroids, you can arrange things in pathological ways, like this union of two lines, where all of a sudden you're forced to have all your planes having unbounded size. But what this is saying is that almost no matter how you arrange them, you're going to have this absolute bound. So I'm going to more or less show you how we proved this planes result, or at least I'm going to show you quite a bit of the proof. But before we get into planes, we need to talk about lines, average line size, because that's really the natural place to start with a problem like this. So what do we know about average line size? So again, the question is, if I give you an arrangement of points in real space, and we can assume that we're in the real plane here, is the average size of a spanned line bounded by an absolute constant? And the answer is yes, and this was proved by Melchior around 80 years ago. And he proved this fact with a very impressive bound of 3. So the average number of points in a spanned line, so long as your matroid isn't sitting in a line, then the average is going to be less than 3. And 3 is best possible. So this is quite an impressive result. This result is only for the real representable matroids, though, but it was extended to the complex setting by Hirzebruch in 83. And I should have written there that Hirzebruch's bound was 4, which is also very impressive. I don't know if 4 is best possible, but the bound for complex does need to be strictly greater than 3, so it's somewhere between 4 and 3. It would be interesting to know what the best bound is, but still, this Hirzebruch theorem is very impressive. So these two results really provide the starting point for everything I'm talking about today. These results inspired all of this research for us, particularly because, at least speaking for myself, I find these theorems kind of surprising. Regardless of the bounds, I wouldn't have suspected results like these to be true, but so we were kind of struck by these theorems and asked ourselves, well, what about planes? What about flats of general rank, and so on? So that's kind of how it all began. I'm going to quickly show you the proof of Melchior's theorem. The proof of Hirzebruch's theorem is quite hard. It relies on very sophisticated algebraic geometry. But on the other hand, the proof of Melchior's theorem is really short, and so I'll show it to you not because it has anything to do with the rest of the talk, but because I find it really cool and I think it's worth advertising. Right, so the first step with Melchior's theorem here is, so remember you're considering a finite set of points in the plane, not all sitting in a line, but because that's a finite set, you can assume that you're in the projective plane. And the reason for doing this is so that you can dualize. So projective planes have a property called duality, which basically says that because of the symmetry in the incidence relation between points and lines, you can kind of flip that incidence relation, and in so doing, any statement about lines and their points and their spanned lines can be translated into an equivalent statement about lines and the points at which they intersect. So rather than considering an arrangement of finitely many points in the plane, we're going to consider an arrangement of finitely many lines. So something like this. This is just a small example here. But in the dual setting, what we need to show is that, so we look at these intersection points in the arrangement, and what we need to show is that the average number of lines to which these intersection points are incident is less than 3. It's the dual version of Melchior's theorem. But now the trick is to just use graph theory. So as you can maybe kind of see, this set of intersection points, if you view those points as vertices, you have a graph drawing in the projective plane, these line segments as edges. And we know that such graphs have bounded average degree, and that's how you prove the result. So I think that's a really nice proof.
So is this result can be extended to oriented matroid? This seems like...
Can it be extended to oriented matroids?
Yes.
Yes, I believe it can. Yeah, that's a good question.
Maybe duality is a little bit tricky, but at least this statement about curves intersecting can be extended. I'm not sure about that.
Yeah, that's maybe a good point. How the duality goes through, because you'd be dealing with pseudo lines rather than lines.
What?
When you have an adjoint, that means you're duality.
There's some kind of duality,
Yeah.
but is it the natural?
Adjoint is exactly the same duality that exists.
Okay, yeah, that's a good question though. Maybe we'll discuss and clarify that after the talk, maybe. All right. So yeah, I really like this. Oh, sorry.
No.
Oh, you okay?
I was just thinking.
Yeah, so I really like this proof. Of course, who doesn't like a proof that's so short and elegant? I also really like it because it demonstrates the power of graph theory. Right? You're just using fundamental graph theory to prove something that I think is pretty cool, that doesn't really have anything to do with graphs. But unfortunately, I don't know a way of doing something similar for planes. I mean, maybe there's a way of using the Euler-Poincaré formula for hyperplane arrangements or something like this, but I haven't figured out how to do it. So basically, what I'm saying is, before we tackle the problem of bounding average plane size, we should figure out a new way of bounding average line size, hopefully using a technique that we can generalize and extend to the planes problem. And we're going to use some geometry to do this. So one of the maybe drawbacks of this proof of Melchior's, as nice as it is that it's maybe not so intuitive in the sense that it doesn't give you the best idea of what's going on geometrically. So we are going to use a very illuminating result, a very classic result from discrete geometry called Beck's theorem. So Beck's theorem basically characterizes when your matroid has quadratically many lines. So what it's essentially saying here is that either your matroid has a line which is as large as you like as a fraction of the number of points, or you have quadratically many lines. And I think this is a really, really nice theorem because it's just giving you so much structure just by putting a modest bound on your number of lines. A huge line, a line that's as big as you like, that's a lot of structure, and we're going to exploit that. But how are we going to use this for this average problem, right? So bounding the average size of lines in your matroid is equivalent to showing that the number of lines in your matroid and the aggregate size of the lines in your matroid are within a constant multiple of each other. Right? So the first thing we need in order to tackle this problem is a really good approximation for the number of lines. And because any matroid can have at most quadratically many lines, when you find quadratically many lines, that's as good of an estimate as you can ask for. And so that's how we're going to use Beck's theorem. So the actual estimate we're going to give is this one. So we take a largest line in our matroid, which we'll call L star. And we're going to show that the number of lines in the matroid, that's what I mean by script L there, that's the set of lines. So the number of lines in the matroid is at least n times, a constant multiple of n times n minus the size of that largest line. So the way we prove this is, like I said, we use Beck's theorem to get structure. So we can use Beck's theorem immediately, because if we get quadratically many lines, we win. So you can view your matroid as consisting of this massive line, again, as big as you want, and this tiny set of leftovers. Okay. So looking at this quantity on the right-hand side, what you want to do is go through each point in the leftover set and show that it's in omega of n lines. Right? So the only issue you have to be careful about there is double counting. But let's just see how we do this. So let's take a point from the leftover set, and then we're going to consider the lines it spans with points from our big line. And now, because this line L star is so massive compared to the leftover set, you're guaranteed that the vast majority of these lines consist of only 2 points. Right? They're not hitting any other points in the leftover set. Specifically, omega of n, number linear in n of the lines are going to have that property. That's what you get by just taking that line to be really large.
Maybe I mostly it seems like everything looks distinct, but do you have a particular case where these lines overlap, or?
Yeah. So what I'm trying to avoid here, I maybe didn't draw it the best. Like, the thing that can happen is that, say we're looking at this top line here, it could be hitting other points out here, and we don't want to count those lines because we're trying to avoid double counting.
I see.
Yeah. Sorry, did that answer your question?
So the number of lines that doesn't hit any other points in n minus L star is still linear. That's what.
Yeah. Yeah. I maybe could have drawn the picture a bit better, but hopefully that makes sense. But that's how you get, this is how you get the result, right? So there's n minus L star points sitting outside of the big line, and then for each of those points, you just count up the lines that consist only of that point and the line and the point in L star. And by doing that, you don't get any double counting. So that's how we prove the lower bound, and it's even easier to check that this lower bound is best possible. So one way to check this is to just draw the same kind of picture where you have a biggest line and a set of leftovers, and you count up separately the lines that hit the big line and the lines that don't. And in both cases, you get at most n times n minus size of L star lines. Okay, so we have a best possible estimate of the number of lines here. So what we have to do now.
So
Yes.
where we use the R representability, is it?
Where do we use?
Why real representable is important?
I didn't hear you. I'm sorry.
Why this is real? Why the real representability is important?
To use Beck's theorem. Yeah.
Okay.
So he asked where we're using real representability here, which is a very good question. It's in the invocation of Beck's theorem. Beck's theorem relies on. Beck's theorem does not hold for matroids in general. Something special about real representable. That's a good question. Thank you. Right. So in order to finish to bound the average here, now we have to show that the aggregate size of the lines is also bounded above by a constant multiple of this estimate. And to do that, we're going to consider a similar sort of picture, but what we want to ask ourselves is what this quantity on the right-hand side is counting. And you can see that it's counting the set of ordered pairs of elements where the second one is not in your largest line. I'm using the same notation as before, where L star is the largest line. Okay. And then you go through and you consider the same kind of picture. In this case, we can't assume that L star is as big as we want, but we don't need to. And in order to get this bound, because distinct points span unique lines, what you want to do here is show that every line in your matroid contains lots of pairs which contribute to this count, this set script T. Now, a line that doesn't hit L star, that's really easy. Any pair of elements from that line forms a pair in script T, so you're getting lots of pairs there. And so the worst case thing to kind of consider here is a line that does hit L star. But in this case, you just fix its point in L star, and then go through each of the other points here, and they're all in script T. So the point is that because for each line you're getting at least its size minus 1 pairs contributing to this count here, you get that this aggregate size of L minus 1 is bounded above by the size of script T. I'm not counting the big line L star here because L star doesn't give you any pairs, but that's fine because that line can't hurt us on its own. And also subtracting off a minus 1 doesn't hurt us either because we're fine with taking a constant multiple. So that's how we prove the aggregate bound. Maybe I went excuse me. Maybe I went through that part a bit quickly, but hopefully this is kind of making sense. So yeah, so we've bounded the aggregate and we've lower bounded the number of lines. They're the same up to a constant multiple, so that means that the average size of a line is bounded. So we now have two proofs of this fact. We have Melchior's slick. Sorry, I was not expecting to be clearing my throat this much. I don't know if that's nerves or what. Yeah, so we have two proofs of this fact. We have Melchior's slick graph theoretic proof, and we have this more geometric proof that uses Beck's theorem. And this geometric proof is what we're going to try to generalize in order to prove the theorem about planes. But before we can do that, we need to talk about the things that can go wrong. Okay, so as I've already pointed out, the average plane size is not always bounded. So we saw this example of the two skew lines having unbounded average plane size. And what we're going to prove is that this is the only thing that can go wrong for planes. But as you can imagine, when we go to higher rank flats, the complications that can arise become even more numerous. So we need to get a handle on the kinds of things that can go wrong for these average problems, so that we can figure out which matroids are degenerate and then forbidden. Okay, so fortunately, there's already a notion of degeneracy that's well studied. So we're going to call a matroid K degenerate if there is a collection of flats in the matroid, each with rank at least 2, which cover the ground set, and whose dimensions sum to less than K. Right? So rank in a matroid can be thought of as dimension plus 1. So that's why we have this rank minus 1 thing in sum, saying that the dimensions of the flats sum to less than K. Now, this definition might look a bit complicated. It's certainly difficult to see kind of what it's saying at first glance. But note that this does generalize the kinds of degeneracy we saw in lower rank. So a 2 degenerate set is a line. A 3 degenerate set is either a plane or the union of 2 lines. And like we saw when bounding average line length, we had to forbid the thing from being just a line, of course. And for average plane size, we have to forbid the matroid being a plane itself or the union of 2 lines. Okay. So this is generalizing those notions. But this is an abstract definition, so the question is, why is it so bad when it comes to averages? And what makes degeneracy bad is essentially this fact. So if I have a K degenerate matroid and F1 through Ft here form this cover of flats per the definition, then every rank K flat in your matroid is forced to contain one of those flats in the cover. So to see this, just take a basis of your rank K flat, and then by submodularity of the rank function, we get that the sum of the ranks of B with each flat in the cover is at least K. But then you just apply 2 with the pigeonhole principle, and that forces for one of the indices I for the rank of B intersected with Fi to be at least the rank of Fi. So that means that B spans that flat. So the point of this remark is that with K degeneracy, we're seeing a similar kind of thing to what we saw with the 2 skew lines, right? So with 2 skew lines, we saw that every plane was forced to contain one of those lines. And here, in a k-degenerate matroid, every rank k flat is forced to contain one of these guys from the cover. And this is a problem for averaging, because if you just take all of those flats in the cover to have size linear in n, you can again make your average arbitrarily large. So degeneracy is bad, and it's something that we need to forbid in order to bound the average. Now, I'll get back to rank k flats in a bit. I am going to talk about the average size of general rank k flats, but as I said, I want to go through this proof for planes. So again, our geometric proof of bounded average line size fundamentally relied on Beck's theorem, and so we need a version of Beck's theorem for planes. So we get this. This was proved by Tao Do, and it uses this same notion of degeneracy that we just saw. So what this theorem is saying, and I've stated it in full generality here, but we're only going to use it for planes, i.e. the k equals 3 case. But what it's saying is that essentially either your matroid has on the order of n to the k rank k flats. This is what I mean by script f sub k, set of rank k flats. Or you have a k degenerate set, which is as large as you like. Okay, so this is a very nice theorem that's giving your matroid lots of structure, and this is going to play the role of Beck's theorem in the proof of this this theorem about planes.
What's the notation of the last line?
Sorry.
Is plus k, is that
Are you talking about this?
plus 3 or?
This
yeah,
one?
yeah.
That is a script F. Yeah, totally okay to ask me about my writing. Yeah, this is the problem with making up notation without telling people about it. The script F sub k denotes the set of rank k flats. Yeah. Right. So for planes, we're going to follow a similar sort of strategy as before. So remember, the first step is to get a really good estimate on the number of planes. And our estimate for the number of lines relied on this choice of a largest line. In this case, what we're going to do is pick a largest 3 degenerate set in the matroid, and then we're going to choose a largest 2 degenerate set, i.e. a largest line sitting inside that largest 3 degenerate set. And then we're going to obtain this approximation, which sort of generalizes the one that we saw for lines. So we'll prove this by case analysis on the structure of the 3 degenerate set x3. So remember, a 3 degenerate set is either a line or a pair of skew lines. So we're going to consider those cases separately. And recall also that by Do's theorem, we can assume this set to be as large as we'd like. So basically, our matroid is going to consist of this massive structured thing together with a tiny set of leftover points, and then we'll do a sort of similar flavor of analysis as what we did for lines. But actually, the first case we'll be considering is when this line x2 is huge. And by huge, I mean 3/5 the size of the matroid here. It's It's pretty huge in my books, but really any coefficient that's greater than 1/2 will work here. So we have this massive line, and the way we're going to count planes in this case is by counting up lines which are skew to x2. So here's that line, that red line is skew to x2. And then for each of those skew lines, we're going to count up the planes that it spans with points in x2. But again, we want to do a similar kind of thing where we avoid double counting. And we'll do this in a similar way as before, where we're just going to count those planes. So just looking at this red line, we're only going to count the planes that consist only of the red line and one extra point taken from x2. And because x2 is significantly larger than 1/2 the size of the matroid, linearly many of these planes are going to be good in the sense that I just described. You have so many planes here that you have a very good proportion of them which avoid hitting any other point in the leftover set. So those are good planes for counting. So looking at this quantity, we have a fraction of n good planes for each skew line. So what we need to do now is show that we have enough skew lines here. We need n minus size of x2 times n minus size of x3 lines skew to x2. And we get this found by reducing to the rank 3 case and applying our earlier lemma. So we do this by a projection argument. So the projection argument is called principal truncation. And basically what you're doing is you're adding a plane in general position, and then you're going to project everything onto that plane in such a way that x2 projects to a point, and everything else in the matroid projects freely. So, in a sense, you're preserving all the other structure. You're preserving all the structure that's skewed to x2. So the point is, in this truncated thing here, all of the lines in this matroid that don't hit x2, those are in 1-to-1 correspondence with your skew lines in the original matroid. So we just need to count up. We need to count up those lines. And we can use our earlier result to do this. So basically we have n minus size of x2 points in here. And the real beauty of doing this principal truncation is that by our choice of x3 being a largest 3 degenerate set, x3 is automatically going to be the largest line in this truncated matroid. So when we apply our lower bound for the number of lines, we get the quantity we want. And then those lift back to skew lines in the original matroid. All right. So from now on, I'm going to assume that this largest line is bounded in size as a fraction of n. So note that that means we can use Beck's theorem, and we will. And then we have to break into the cases where x3 is a plane and where x3 is the union of two lines. So we'll assume that it's a plane first. So we have this picture of our matroid where we have this plane that's as big as we like, and then this leftover set. All right. So the way we're going to count this time is we're going to go through each of the points in the leftover set and then take their spans with lines in the plane. And again, so you're maybe starting to get a sense of a strategy that we use kind of over and over again to avoid double counting. We want to show that there's lots of lines well, so we take a guy up here, and then we want to find lots of lines whose spans with that guy form a plane consisting just of that line and just of that one. And that's how we're going to avoid double counting. But in order for this to work, we need for there to be lots and lots of lines sitting in the plane down here. But for that, we just use Beck's theorem, right? The size of the largest line is bounded. So that means we can use Beck's theorem, and also it's bounded as a fraction of n, and the size of x3 can be made as big as we like as a fraction of n. So we can apply that down there and get quadratically many lines. All right, so now to do the counting, we go through each point here, and then take spans with the lines down here. So that's what we're going to do. So we'll fix a point x and consider all the planes formed by those spans. And again, like I was saying, we just want to count the planes that consist only of x and the line. So what we're going to do is throw away the bad ones. Okay? But the way we do this is, well, the reason we can do this is that each other point from the leftover set can be contained in at most n of these planes. All right, so that means that there are at most n times the size of the leftover set bad planes that we're going to throw away. But because the leftover set can be made so tiny, we can make this a very tiny fraction of n squared. And then we have some fixed fraction of n squared over there, which means that we're going to obtain quadratically many good planes.
So how you figure out that the size of x is linear? To apply
The size of
x3.
x3?
Yes.
That was by Doe's theorem. Right, because that was the analog to, that's the higher dimensional version of Beck's theorem. So yeah, yep. All right, so that takes care of that case. So the final case to consider is when x3 is the union of two lines. And I'll probably go through this case a little more quickly because you're probably starting to kind of get the picture of the strategy we use here. We basically do the same thing in every case. Basically, you have this big structured thing, and then you go through each of the leftover points and only count those planes which hit the leftover set in exactly one point. And we're going to do the same thing again. The only thing we need to observe here in order for this to work is that both these lines are size linear in n. And this is because x2 is the bigger, or yeah, it's the biggest of the two lines, and all of x3 itself can be made really big as a fraction of n. So that forces both the lines to have size linear in n. And then we're going to play the same game we played before, where we just take a point from the leftover set. Then we're going to look at how it relates to one of the lines, and because the line's so big, we're only going to pick the 2-point lines. And then for each of those 2-point lines, we're going to take its span with points in the other line and do the same thing and only pick the 3-point planes. So, yeah, so I maybe went through that one a bit faster, but it's really the same type of strategy we've seen a few times already. Okay, so that's it. That's the proof of this lower bound. We've handled all the cases now. So the next step is to bound the aggregate plane size. This is not something that I have time to do today, but yeah, to bound the average, you now have to show that this aggregate size of the planes is bounded by the same estimate we just got for the number of planes to a multiplicative constant. to do this, you use basically a refinement of the strategy we saw in the lines case. But yeah, I'll leave that for today. Okay, so yeah, so we've proved, well, that's quite a bit of the proof of how we proved this thing, how we bounded the average plane size. And in the last few minutes here, I'm going to talk about flats of arbitrary rank, flats of rank k. But our results for higher rank flats are generalizations of two corollaries of our theorem here. So the first corollary that I want to point out is that if I give you a real representable matroid of rank at least 5, then the average plane size is bounded by an absolute constant. And this is just because if you bump up your rank by 1 to rank 5, when you truncate the matroid to rank 4, you cannot possibly obtain a union of two lines. Okay, so then you just apply our theorem and you get the bound on the average plane size.
Sorry, I didn't understand. What did you say when you truncate to rank 4?
Yeah, so yeah, truncation is it's a matroid operation, but it's also
That was the thing, like the result when you truncate the rank 5 to the rank 4, then what happens? I didn't know.
When you have a rank 5 matroid, the truncation of that matroid to rank 4 can't be the union of two lines. Yeah, it's just not possible. So then you can apply a theorem. Yeah. So yeah, you can kind of think of this corollary as saying that when you take your rank sufficiently high, you get bounded average plane size, and so that's something we're going to generalize. And then the other consequence is that, well, we saw that average line size is bounded, and we now have that average plane size is bounded. So if you're rank 4, this means that the average size of a flat is bounded. So now you take the average over all your flats, and you also get that that's bounded. So this is the other thing that we'll generalize. Okay, so we get our higher dimensional results using a really nice theorem of Ben's. But just a bit of notation first. We'll let GI denote the size of a largest I degenerate set in the matroid. So largest degenerate sets have been kind of a theme so far. Remember, in the planes proof we took a largest 3 degenerate set, and the lines proof we took a largest 2 degenerate set, and now we're going to do a similar. We're going to get a similar count here. This is a theorem of Ben's, and basically this says that for any k, we have this constant called ck, so that if your matroid is at least ck points away from being k degenerate, right? You have at least ck points outside of your largest k degenerate set, then you get this really nice estimation of the number of rank k flats. And this is this estimation is generalizing the kinds of things we've seen before, where you've got n times n minus the size of a largest 2 degenerate set, and so on. So now what we do is we combine this with this aggregating lemma that we proved. So in particular, you take d to be the largest, take the largest number d for which your matroid is not d degenerate, and then you get this this bound on the aggregate size of the rank k flats. And when you look at these two things together, this is sort of telling you immediately that given k, if you have a matroid of really, really high rank, then you're going to get bounded then the average size of a rank K flat in that matroid will be bounded. So the reason for this is this constant CK. So basically, like, take the largest possible rank of a K degenerate set, and then bump up that rank by CK, and then that matroid cannot possibly be K degenerate. Sorry, it can't possibly be K degenerate, but it also has at least CK points outside of its K degenerates. So that tells you that when you have really high rank, you get this good estimate of Ben's. And by the way, Ben also proved that this is a best possible estimate, regardless of degeneracy. And then you also apply the aggregating lemma, and you get the bound on the average.
Your aggregating lemma is stronger than just showing that that's best possible, right? Is that
Yeah, I suppose so. Yeah. Yeah.
because you're adding up the number of points on each flat, not just put one.
Yeah,
size
exactly.
flat.
Yeah, so Ben was just pointing out that this is a bit stronger. This is stronger than this as a best possible bound. Yeah. We needed to count just up to D, essential dimension,
I see. Is it
for the,
no,
yeah.
it's the same as K. I'm sorry.
Yeah, no worries. Yeah, no, we did that mostly for the purposes of what I'm going to show you next, which is bounding the average flat size. Right. So yeah, you take your rank really high and you win. But if you do it just, we actually got a rank bound of 2k minus 1 just by doing things a little bit more carefully. But I won't explain that. But yeah, that's, and this is a generalization actually of the rank 5 thing we saw. Okay. So yeah, I'm just putting this lemma back up again just for clarity. So the other thing we want to do is show that for any given R, if I have a matroid of rank R, then the average size of a flat is bounded above by a constant depending only on R. And this is something that's not, once you have these two results, this is something that's not particularly difficult to obtain, but there's just certain intricacies that are a bit hard for me to describe, especially since I'm hoping to wrap up in a few minutes here. But at a very high level, what you're going to do is use Ben's theorem here to get a lower bound on the total number of flats. And then you're going to go through each possible rank in your matroid and apply this to every one of those ranks. And then you aggregate those all together and you get your bound. So yeah, that's maybe a bit hand wavy, but yeah, the upshot is we get this result. So we get bounded average flat size for matroids of any rank. And I think it's time for me to wrap it up there. So thank you for your attention.
Thank you. Any questions?
This obvious question is like, what kind of related open problems?
Open problems?
Yeah.
Yeah, there's quite a few. If you look at the paper, there's a whole slew of conjectures that Jim came up with, which are really interesting. A lot of them are about the bounds, like there's questions about average line length. We say length sometimes. I've been trying to say size for this talk, but the average size of a line, getting really good bounds on that. Getting good bounds on the average size of a flat. But yeah, those probably pretty challenging, but interesting.
Did you ever calculate an explicit bound on n in there? Or do you
No.
have any sense of how
No.
much it might be?
I like. Yeah, that's a good question. It's something we, I guess, didn't see a point doing for the paper, because it would have been pretty large, not outrageously large, but probably as the grad student, this is probably something I should have tried to go through and check by now. I want to say that might be less than 1,000.
Oh, okay. So like,
Yeah,
yeah,
it's not. It's definitely not.
Something crazy.
It's not outrageous. I mean, the interesting thing is, yeah. So, a lot of this relies on a theorem from discrete geometry called the Semiretti-Trotter theorem, and there are some good bounds for that. And when you invoke those, throwing that into here and calculating, you probably get something decent. So it would be because of work other people did mostly.
And if you had to guess what the true number would be, what would you be more likely to be?
So I'm pretty optimistic, and that's, I mean, our guesses have been proven to be wrong before, but I would say less than 7 because I'm an optimist. And we know that there exists a matroid, a real representable matroid whose average plane size is 6. And for complex, it tends to be a little worse, but it's probably still pretty good for. I'm gonna stick to talking about real because, yeah, the complex stuff, I'm forgetting some things at the moment. Gets more complicated.
So you have for the C sub k in my theorem, you showed that it's 0 for C sub 3 is 0.
Yeah.
And you also showed that C sub 6 is not 0 or something like that. C sub
Right,
7.
right. Yeah, so yeah, that's a really good point, and that's something I wanted to mention during the talk. But so what Ben just said is that our theorem about planes shows that his constant C3 is 0. We also saw that C2 is 0. But yeah, as a matter of fact, those constants definitely are not 0 in general, and I think it's C5 that we know to be non-zero, and then the matroid is rank 6, so you're looking at rank 5 hyperplanes in that thing, and yeah.
What is this C3 or C2 or C5?
Those are the constants from
The last year?
Lund's theorem.
Ah,
Yeah.
You thought about the asymptotic growth in K?
Sorry?
Do you have any idea of what the asymptotic growth of that function is in terms of K ought to be?
Which function?
C sub K.
No, I haven't. That's an interesting thing to think about. I haven't thought about that.
So for the complex case, every theorem, so if I just replace real by complex, then you have the same theorem? Or except some minor changes, or what's
No, you get all the same theorems. If you were to try to calculate the bounds, those would probably be different, but you do get all the same theorems. Again, not because of anything we did, but because all of this kind of goes back to the Semiretti-Trotter theorem, which was proved in the complex case by Toth.
is there any some result for the finite field?
Sorry, say that again?
Finite field?
Finite fields. I mean, you definitely have to impose some condition, because for matroids representable over finite fields, you just look at projective geometries, and right, so the size of the flats grow with the size of the field. So yeah, you wouldn't really have any hope there unless, I mean, maybe there's some kind of interesting condition you could impose. But it's a good question.
There is a kind of famous conjecture, which is that the summary trotter should hold for for reasonably small sets in a finite field. It's actually known to hold for very, very small sets.
Okay. Yeah.
And
I've heard about this. I'm not super familiar with it, but yeah, that would be a thing to think about regarding your question. Yeah. There are, like, call it like a partial Semeretti Trotter type result. Yeah. So those do exist for finite fields, but
if the size of the point set is smaller than the characteristic of the field, it's
like significantly smaller.
not even that. Yeah, I'm not sure exactly what the bounds are. Say you have p squared points roughly in your geometry, and you have fewer than p points. That might be enough. If p is a prime.
Okay.
Maybe we should continue discussion after. All right. Yeah. So let's thank the speaker.